The other is a function of the two polar angles, theta and phi. Okay. All right. Now, so let's set up the problem, the model we'll be using. So we've got a particle. Now forget about spin for the moment, right? Simplify things. This particle has mass m, and it's in an attractive potential. For example, maybe you're talking about the electron as your particle. This would be the mass of the electron, and it's attracted by the nucleus. So it's the nucleus, because the charge on the protons is positive. Electron charge is negative, so there's an attraction. Opposite charges attract. Okay. So now assume this particle is feeling an attractive potential V, the potential V that's just a function of position r. That's all. Forget no spin. And assume that this potential is time independent. Does not depend on the time. And in that case, when you solve Schrödinger equation, you expect stationary states. Now, I talked about stationary states earlier chapters. A bit of a reminder here, refresher. A stationary state, what is that? It means that the probability density you get from the state, the wave function, when you square it, remember, it gives you a probability density. That probability density is independent of time. It's not a function of time. Okay? So if the probability density is time independent, the wave function that you used for it is called a stationary state. State wave function, same thing. Right? So a stationary wave function or a stationary state has a probability density that's independent of time. Okay, refresher. Okay, now let's assume this potential. So it's created by some central body. Well, the obvious example would be the nucleus in the context of talking about an atom. And say the central body has big mass m. So, for example, the Coulomb field, just the electrical potential generated by an atomic nucleus. Right? Now, you're talking at two, like in the simple case of a nucleus, let's say the hydrogen atom. So you're talking, the nucleus then is just one proton, large mass compared to the electron, which is about 1,000 times lighter. The electron's quite light compared to the proton. So you have the nucleus, sort of relatively heavy nucleus, and a light, small mass electron. So a two-particle system. Now, in classical mechanics, just a minute, I don't know if you've done this. Well, for example, one of the master's level courses, I keep saying this, one of the master's level courses that I'll be giving will be on classical mechanics, because it's such an essential basis for quantum mechanics, Hamiltonians, Lagrangians, stuff like that, that we will be using in quantum field theory. Quantum field theory, QFT, it's just all about Lagrangians, right? And particle physics and so on. So you need a really good basis on what Lagrangians are and Hamiltonians and so on. So I will be teaching a master's M1 level course on classical mechanics with this text. Now, chapter 3, the beginning of chapter 3, not that it means much. The title of that chapter is the two-body central force problem, and the first section of that chapter, 3.1, is called Reduction to the Equivalent One-Body Problem. And now, if you've not done classical mechanics and you don't know what I'm talking about, it doesn't matter much. It's just a slight modification. But you can effectively treat two bodies attracting each other as just one body. Like this point over here, maybe the origin of your axes, x, y, z, and here's the origin, 0, right? And here are your two bodies, say A and B. You can treat the classical dynamics of those two bodies effectively as one body. and with a modified mass. So if you have a little mass and a large mass, a little m and a large m, this equivalent treatment of this two-body problem into a one-body problem, the equivalent mass then becomes what's called the reduced mass in this form. There's a formula for it. This is the reduced mass. And we'll modify the Schrödinger equation slightly in this special case when we just have two masses, two particles. Like, for example, this might be the electron mass and that might be the proton mass. So you have a two-mass, a two-particle problem. And then from classical mechanics analogy, you can use the idea of a reduced mass, which is this. Now, if you haven't done any classical mechanics and you don't know what I'm talking about, don't worry. The only thing that gets modified in the Schrödinger equation that you're used to is instead of having m here being the mass of the electron, it's now the reduced mass, this mu here from here, right? So it's the only difference. So if you haven't done the classical mechanics, if you don't know how to reduce like a two-body problem to a one-body problem using the reduced mass technique, don't worry too much. But like I say, I will be teaching a classical mechanics course, right? Now, in the case of the hydrogen atom, where the mass of the proton is about 1,000 times heavier than, more mass than the electron. So this little m here becomes negligible compared to this. So these two m's cancel and you're just left with little m. So effectively the so-called reduced mass just becomes little m. Right? That's just simple math. Right? Okay. So go way back to chapter 2. Now, here's your Schrödinger equation. Here in this form here, it's written in the form of a eigen equation. So here's your operator, your Hamiltonian operator, wave function, or eigenfunction is eigenvalue. In this case, it's the energy. So this is the energy eigenfunction, right? Here's your eigenfunction again, right? U. Now, we're being more general now. We're not just looking... See, in chapter 2, we did a very simplified form. We just were concerned about R, the position. But now that we've done angular momentum, previous chapter, we can now bring out the big guns and talk about the wave function now. It's not just a function of R, it's also a function of polar angles as well, theta and phi, okay, the two polar angles. Now, you may remember from earlier chapters the Hamiltonian. If you're not using x, y, and z, if you're using the spherical polar coordinates r, theta, and phi, then your del squared, that's like an upside down triangle squared, from vector calculus, and I'll be giving a course, as I keep saying, I'll be giving a course, I'm not sure still yet, it'll be a mini course or not, but I'll be giving some lectures at least on vector mechanics, vector calculus. And the del squared operator that features in the Hamiltonian, so just verbally it's, what is the Hamiltonian with the del squared? I think it's h bar squared over 2m, is that right? Del squared, and then plus v, the potential energy, all times the wave function equals E times the wave function, something like that. Maybe I've got a missing I in there somewhere, I think. I h bar. Oh yeah, I h bar d psi by dt. Right? Well, in the time independent, the st form, it's like this, right? And that del squared from vector calculus, that del squared is all this, right? It's all the stuff in the square bracket. That's your del squared. Now that's pretty hefty stuff, right? If you've that's not at all obvious you would need to know, where you need to derive that from vector calculus, and hence, I'll give at least a mini course on that. But for the moment, just assume that the content of this square bracket, it's just del. It's the operator, the vector calculus operator del squared. Okay, plus the wave function equals energy eigenvalue wave function, or eigenstate. Alright, so that's just what I'm saying. What's in the square brackets is just your del squared. Now, this whole thing can be simplified, of course. And the critical thing to notice is, if you've been studying this closely, especially previous chapter, you may notice something a bit curious, and that is this term here, this term plus this term. Does that look familiar? Haven't you seen that before somewhere? And the answer is yes. This plus this is almost identical to the angular momentum squared, L hat squared. Right? And we're going to use that. Instead of putting this in here, we'll put in L squared. And so we'll have L squared U. And that means we have a kind of eigenequation for the angular momentum. And that means instead of all this stuff, we can plug in the eigenvalue times the eigenfunction. So it simplifies down a lot. So in a sense, this term here, all its complexity, depending on theta and phi, that just simplifies down to a scalar, just a number, eigenvalue, times the eigenfunction. So then effectively you're just left with the R. You're just left with the R term plus some angular momentum eigenvalues, L into L plus 1. Well, I'm getting a bit ahead of myself. So you'll see that simplification occur in the next session.